Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day, here in my virtual classroom. Alright, step on inside, and in the Integrated Math 2 Big Ideas Math textbook, flip to section 1.4 and check the PDF down below and the link for properties of exponents and the many problems that we're going to be doing here. Thankfully, on my end, I think they're more of drill and kill, less graphing, and more just doing. I haven't seen them all, but knowing properties of exponents, that's the kind of thing that's going to happen. Maybe have your calculator ready as well, because with exponents can come big numbers if they're doing simplifying that way. We'll run through a lecture overview looking at what kinds of properties they have in mind for us, and then we will go to the problem set. So let's begin by taking a look at, we will learn to use the zero exponent and negative exponents, the properties of exponents, so anything else that's involved with them, and solve real-life problems involving exponents. So, with the zero and negative exponent in mind, make sure you know what an exponent is. If you say a to the b power, the b is the exponent. I can't write, I'm sorry. That is an exponent. And a to the b power means a times a times a times a, whatever. There would be b amounts of a's multiplied together. 5 to the third power equals 5 times 5 times 5. So that kind of thing. If the exponent describes or shows or indicates how many of your value is multiplying to itself, then it's important to understand that when you multiply that number over and over going this way to the right, going to the left should then indicate how many times you divide by it, or as I sometimes say, you multiply in the denominator. So if you don't multiply by your number at all, you have to start from the number 1. And I've done this with tables before. I won't kind of do it now. I'll let this speak for itself. But any number, any non-zero number to the 0 power is 1. With 0, it has to do with dividing by 0. It doesn't quite work. But just assume we're not talking about 0 bases. But anything to the 0 power is 1. Okay. Negative exponents, on the other hand, lead to, like I said, division of that value from 1. Or multiplying by that number over and over in the denominator. 4 to the negative second power is 1 over 4 squared, which is 1 over 16. Whereas 4 squared is 16, 4 to the negative second is 1 over 16. Negative exponents don't mean negative numbers. Once again, they mean how many times you divide your value, not subtract it or add its negative. So that's what those two things mean in that case. They have some examples of that, which you can see here. 6.7 to the 0 power is 1, 1,000 to the 0 power is 1, pi to the 0 power is 1. Those are all 1. Negative 2 to the negative fourth is 1 over negative 2 to the fourth, and negative 2 to the fourth is negative 2 times negative 2 times negative 2 times negative 2. Two sets of pairs of negatives equals a positive. It still gives you that 1/16. Simplifying expressions. So you see this expression here, 4x to the 0 over y to the negative third power. Now, something that they can't really show you that I'm going to be doing a lot of is when it comes to simplification, there are a lot of things in play, and I can't talk about all of them yet because we haven't seen all the properties, but we shouldn't have negative exponents in our answer. We should combine any sets of multiple instances of the variable that we have, meaning if there's an x here and an x here, somewhere we should find out how they can become 1 and be raised to just a single power. That single power, like I said, shouldn't have negative exponents or fraction exponents or anything like that. So there are certain things involved with the simplification of, and the positive exponents is among it. X to the 0 power is 1. 4 times 1 is 4. So if you ever see me cancel out something like that, it's a result of it no longer being visible. Y to the negative third, because it's in the denominator, dividing by something in a denominator becomes multiplication in the numerator. So now you see it up top, x to the 0 is still there, but now you see it up top here as a positive exponent as a result of having been negative to begin with. And some other examples there, but we'll be doing some of our own. All right, let's take a look at a couple more properties that they have. Product of powers property, quotient of powers property, and power of a power property. You'd be forgiven if you don't remember those names because I don't always as well. I know the properties themselves. Within the name, the property idea makes sense. Product of powers means there are two things with powers that you multiply together. They need to have the same base though, and that's also going to be true for when we're talking about quotient of powers. If they have the same base, we can simplify their appearance. 4 to the 6th times 4 to the 3rd. It is not 4 to the 18th. You don't multiply the 6 and 3. Rather, you add the 6 and 3, and you get 4 to the 9th. The reason is, if you think about it, and in fact, this is an example. Here's the algebra. When you have the same base and you have exponents, whether they're the same or different, you would keep that base and add the exponent. The reason is because, once again, exponents describe how many times you multiply a number to itself. What happens when you multiply 6 4s together times multiplying 3 4s together? The ultimate question when simplifying this is, how many 4s are multiplying together? The answer is 9. You count them up. They add together. That's why. So don't make a mistake on, I mean, we're going to be doing them together. I'm not going to explain this again. I'm doing it in lecture form. Don't make the mistake of seeing multiplication and assume it happens to do with every number under the sun. We don't put 4 times 4 and make it 16 if we're going to use the exponent portion, and we don't multiply the exponents themselves. If the exponents describe how many times you are multiplying something, then you add those exponents together if you're multiplying within. See, 4 to the 6 plus 4 cubed doesn't simplify to something with 4 to some power, but multiplying them does. Quotient is the same kind of form, only with the same base, and you divide these, you will end up subtracting the exponents. Something you're going to see me do often as opposed to this, just to kind of get it there and ready to go, is I'll kind of do, again, a canceling fashion. If you divide all three, here, let me show you this way. 6 4s are multiplied on top, 3 4s are multiplied on bottom, and 4 over 4 is 1, 4 over 4 is 1, 4 over 4 is 1. So what you'll kind of hear me say in its place is all 3 4s on the bottom divide out, and 3 of the 4s multiplied on top are gone, and there's still 3 that are left. Right, so there's the subtraction. That's how you're left with 4 to the 3rd power. And by the way, you're generally expected to then evaluate this. That becomes 64. So you're generally expected to do that within. So that's the property that you'll see for, quotient of powers, where you subtract the exponents. I do it in kind of my own way. And the reason why I kind of do it this way is because not only does it save me a step of needing to write this, but also if it leaves me with more exponents in the denominator, it doesn't leave me with a negative exponent in my subtraction, where then I have to do another step after that. Once I know there are a few 4s in the denominator left, then I'm taken care of. They're still positive and they're good. You'll see what I mean when we do some of them. And finally, the power of a power property. So this one here, and I call it the same thing. I guess that's because it's its name. But you see this 4 to the 6th to the 3rd power. Technically, it's not the 6th that's the 6th that's to the 3rd power. So it's not the power that's raised to a power. It's not 4 to the 6 cubed, mind you, like that. But 4 to the 6th. 4 to the 6th is being cubed. Anyway, if you think about what this means, this is 4 to the 6th times 4 to the 6th times 4 to the 6th. 6 4s multiplied times another 6 4s times another 6 4s. That's 18 total 4s multiplied. That's why you multiply those two guys here, and then you'll have 4 to the 18th. Now, I'm speaking on the lecture portion more slowly this time, and I think that in turn, in sharpening that axe, we can chop down the tree a whole lot faster when we do the problem set, so I don't have to explain it then, and then you got it covered in the lecture overview. So a to the m to the n power equals a to the m times n power. And I think radical properties are the next section, so I won't talk about it then, but I will talk about it then and describe how this kind of idea still applies to radicals when you have fraction exponents. Anyway, so when you see these 3 examples here, 3 squared times 3 to the 6th becomes 3 to the 8th. You add the 2 and the 6, and notice how they do evaluate the answer. Negative 4 squared over negative 4 to the 7th, both being in parentheses, means it's the same base and all that, and we'll treat it when we're ready. Notice how they do the 2 minus 7, and then turn it into negative 5, and then they have to turn the negative 5 into a positive 5 exponent in the denominator before they evaluate. What you'll end up seeing me do instead in the problems, just so you're aware, is I'll get rid of all of the 2 negative 4s on top. I'll get rid of 2 of the negative 4s down below, and I'll be left with 5 of them. So now I'm at 1 over negative 4 to the 5th at this stage there, without needing to write this step or this step. Keep in mind, when I get rid of this, it's not gone as in no more numerator or the numerator 0. The numerator still has a value of 1 if nothing else exists. Just keep that in mind. Last one, the power of a power. Sometimes I think I say power to a power. Z to the fourth to the negative third. Multiply those to get negative 12. Get a positive exponent out. It's 1 over z to the 12th. There. Okay. And then power of a product. And this also applies to, here we go, power of a quotient. When you have items multiplied within raised to the same power, then you can, I don't want to really say the word distribute, but it's that same equivalent concept of the exponent gets applied to every factor of the product. So a to the m times b to the m power. So that split of 3 times 2, which is also 6, can also be split up in its products there. Same with the quotient, same kind of thing. 3 to the 5th over the 2 to the 5th. You kind of take it into both of those. And of course, you would evaluate them. So you see it there. They always provide these conditions where the denominator can't be 0 and such. We're understanding and accepting of that. They're telling us the rule. Unless there's a problem where they specifically ask, why can't it be? They're not going to try and trick us into a problem and have it. So you don't have to be too cautious of that. But they're just reminding you, you can't divide by 0. All right, so a couple of these exponents that you see here. The first one, negative 1.5 y squared. We would square both the negative 1.5, which is 2.25, and squaring y gets you y squared. This next one's a quotient, a over negative 10 cubed. You get to cube both a and negative 10. A cubed is a cubed, negative 10 cubed is negative 1,000, and you're left with that result. 3d over 2 to the 4th. Now this is good for you to see this here. There is a quotient here, and then within there is a product. The main reason to see this is you have to do 2 different sets. Now you can do it all at once, like I can do like here, here, and here, but what's also important to note is a lot of people see that 3d, for example, and they kind of treat it as a single value. They don't think of it as 3 times d. And I say that knowing how many students I've graded tests and stuff on and seen this before. I warn people of it, and it still happens. This can happen to you. They forget to raise 3 to the 4th power. So whether you do it early on or later, notice that 3 also gets raised to the 4th power. It is multiplying with d. It's part of a product. And then you simplify. And by the way, notice how 3 over 2 couldn't reduce as a fraction. Neither can 81 over 16. If the earlier thing couldn't reduce before you raise them to powers, neither can the later one. No matter how big those numbers get and make you think maybe they can, they can't. And then this one right here, I'll give you an exception to what I tend to sometimes do on these ones. There's this raise to the negative 5th power. Notice how they raise the numerator denominator to the negative 5th, and then they go ahead and swap places to turn the exponents positive. Sometimes I turn the exponent positive first. Meaning, like, I'll simplify the inside by turning this as 3 over 2x raised to the 5th. So, turning the negative exponent positive puts the numerator and denominator, denominator and numerator. Sometimes, I like to get rid of negative exponents as soon as possible. Generally, it's when there's a fraction involved. If there's no fraction, I often don't tend to have a problem with it. Anyway, they raise them to the powers, they keep going, they get their simplified result, which still can't reduce there, despite maybe its possible appearance that you think it could. Okay, and we are then going to look at some real-life expressions and context with these. I don't know how deep I'll get into these specific problems here because every real-life context can be all over the place. This one is volume of a cylinder. I think they'll generally give you the formulas unless they've been uncovered before in the past. I'll make sure to do those with you. I'll tell you what they are when we do problems if they don't tell you. Which the expressions shown represent the volume of a cylinder, where r is the radius and h is the height. They show the radius as h over 2, so we can substitute h over 2 for r. And then you have to keep simplifying, where you square both the h and the 2, and then it becomes a different version of that. This isn't all cylinders. This is just a cylinder where the radius is half of the height. And then it ends up being one of these answers. Looks like this guy right here. So I don't know if that's really real life application so much as it is just there's a cylinder and then we do the same result stuff. But there's that one. And then looks like we have some scientific notation. Now this is something more for maybe your chemistry and physics class where you'll get the introduction of it, or earlier math classes. So I won't speak on scientific notation itself other than they include exponents. And you can treat different parts of scientific notation, such as because it's a product, a times b over c times d can be rewritten as a over c times b over d if, in fact, this helps you simplify things better. Meaning I can divide the single numbers with no exponents with each other. This reduces to 1/5 or 0.2, and 10 to the 8th over 10 to the negative 4th Remember, this can turn into 10 to the positive fourth and multiply up top, and 8 plus 4 is 12, and then you get it simplified in that scientific notation, and then to get a significant figure in the ones place, we can change the 10 to the 12th to 10 to the 11th if we shift this decimal over 10 times more, one place. I don't know what the question was stating, but as far as scientific notation goes, there it is. Okay, and that is the lecture portion of this, significantly longer than we generally do, but I hope that this will make all the other things go faster. Let's start by going over the vocab and core concept check, and then we'll do numbers, I think, 5 through 69. I think it's a whole lot of them. Which definitions or properties would you use to simplify the expression here? Explain. Okay. I don't remember the names. I think it's power of a product and product of powers. So product of powers property. The product of powers one is the multiplication of the two things with powers. So that's where you add the exponents there. Because they have the same base, you're able to do that. That's why. And then I believe, and then power of a product. No, I'm sorry. At that point, now that they're simplified, so here, let's do this. 4 to the 8th times 4 to the negative 4th. 8 minus 4 is 4, so 4 to the 4th, and to the negative second power. The next thing we can do, and you can do it in different order, this is power of a power. And by the way, there are other ways we could have done this problem. We could have done power of a product where you take the negative 2 and apply them to both. I think that's going to be a little messy, though. So power of a power, where then you multiply these two exponents, 4 to the negative 8th, and then the negative exponent property. Negative exponent property. Which becomes 1 over 4 to the 8th, and I don't know what that simplifies to. But we use those as far as simplification goes because we shouldn't have parentheses in our answer. We should only have one set of exponents within any single base item, and we shouldn't have any negative exponents. And then we have multiple of the same base here, so we fused them. Explain when and how to use power of a product property. So this is the one that we didn't use. So this is that like A times B to the M power equals A to the M times B to the M. Power of a product, right? I believe I'm saying that one right. When and how to use it? Well, when you have a quantified product, meaning wrapped in parentheses, when you have a quantified product raised to a power, because every item of that product, every factor is all raised to that same power. So I guess that's the idea. When you have a quantity. When and how to use the quotient of powers property. In this particular case, when you have a quantified quotient raised to the same power there, and then the numerator and the denominator, each get applied. You have to make sure that your b is not 0, but of course it couldn't have been 0 to begin with, so there's that. And then number 4, different word, same question, which is different? Find both answers. If I'm going to apply it the same way that I did last time, let's just call this A. Simplify 3 to the 3rd times 3 to the 6th. We know this is the same as adding the exponents and keeping the same base. So 3 to the 3 plus 6 like this. So I'll call that A as well. These are the same. 3 to the 6 times 3. It's not that they're switched that's the problem. It's that they're multiplying that's the problem. That's a different kind. That's a B. And 3 to the 6 times 3 to the 3rd. They are switched, but that still keeps it the same thing because multiplication is commutative. These are both the same. So B is different. This one's different. All 3 of these are the same. These become 3 to the 9th power. That becomes 3 to the 18th power. And that's them. Okay, so after that, we are going to go ahead and move forward to our whole larger problem set. So get ready to go with these. A lot of them will be hopefully pretty fast within their sections until we maybe start to hit some of the big concept things that are involved. So let's go ahead and move into, boom, this set here. Numbers 5 through 12, where we evaluate the expression. So by evaluate, they mean ultimately come up with the single number. Like if you typed it in your calculator, what would it say? Negative 7 to the 0 power is 1. Now, just one thing I want to state really quickly. Whoops, I don't want to write it over here. One thing to state really quickly, you're going to have to be very careful about the difference between negative 7 raised to the 0 power and the opposite of 7 raised to the 0 power. What I mean by that is there's a difference between this and this. This negative 7 to the 0 power, try it in your calculator, that's negative 1. Because of order of operations, 7 to the 0 is 1. Opposite of that's -1. Because this is in parentheses, this is the number we're raising to the 0 power. That's what gives you 1, as any non-zero number to the 0 power is 1. Anyway, that is number 5. Number 6, 4 to the 0 power is also 1. I don't have much to say to that other than that's what it is. Something happened with the pen I was choosing. Number 7, 5 to the -4th power. So on this one, the one problem with this is with my switching back and forth, because we're not spending a lot of time on each problem, there's going to be a long time in between each problem, relatively, is 1 over 5 to the 4th power. Now you want to evaluate that. 5 to the 4th is 625, so that's 1 over 625. Let's do this. 5, 6, 7. Okay, number 8. -2 to the -5th power. Looks like we're kind of doing one property at a time, if that makes sense. Like we started with the 0 exponent. Now we're using the negative exponent. -2 to the -5th. Now I stated that negative exponents don't mean negative numbers, but this number happened to be negative to begin with. So -2 to the 5th. And -2 to the 5th is -32. So this all becomes -1 over 32. Number 9, we have 2 to the -4th over 4 to the 0 power. Now 4 to the 0 power is 1, so this essentially right now becomes 2 to the -4th over 1, or just 2 to the -4th. Now we can just deal with the 2 to the -4th portion, turn it positive. 2 to the 4th is 16, and this now becomes 1 over 16. Number 10, 5 to the -1st power over -9 to the 0. See, that denominator is exactly what I was referring to before when it came to do with, notice how -9 isn't in parentheses. So it's not -9 to the 0 power, it's the opposite of 9 to the 0 power, which is -1. So this becomes 5 to the -1st over -1, or -5 to the -1st power. And, much like I was just stating, this negative has nothing to do with the 5 as well. The 5 is raised to the -1st power, so this becomes -1 over 5 to the +1st power, which is a long way of just saying -1/5. So a lot of steps, a lot of them unnecessary if you know what you're doing from the get-go. Just make sure that that negative doesn't, if you cancel this part out, that you know that negative's not a portion of it as you move things forward. Number 11, -3 to the -3rd, again, -3 not in parentheses, over 6 to the -2nd power. Okay, this is where, like I said, I like to treat negative exponents positive as soon as possible, so I will move them and make them positive right when I can. Both of them get to switch places. The negative is still involved, just as the whole fraction. So this is now 6 to the +2nd and 3 to the +3rd. 6 and 3 do not divide. They're not the same base, at least not in the way that we have order of operations to take care of. Exponents first, division second. So we have 6 squared is 36, and 3 cubed is 27. So that would be the answer, but we can reduce that fraction, I believe, to -4/3. And we should be done. And number 12, lastly in this little section, we have -8 to the -2nd power over 3 to the -4th power. Let's go ahead and treat the negative exponents first. I'll bring this guy down and this guy up. Notice that the -8 still must stay in parentheses. I got 3 to the +4th over -8 to the +2nd. 3 to the 4th, I do this all the time, is 81. I was like, why am I blanking? And 8 squared is 64. And this should not be able to reduce. We should be good on that. The reason being, 3/8 couldn't reduce. No amounts of 3's multiplied on top and 8's multiplied on bottom will reduce any less or anymore. And that's it. Okay, so that's it for that set. Let's move on to the next set where we simplify the expression. This will contain algebraic values as well as some numbers within. This is the most commonplace kind of problem that we have. I assume. This is the one that I think of when I think of properties of exponents problems. Even some with parentheses, but I don't really see them. And I mean like different groups. Simplify the expression, write your answer using only positive exponents. So let's start with number 13. x to the negative 7th, straightforward. That's 1 over x to the 7th power. And because it's not a number, we can't do anything more with that portion. Number 14, y to the 0 power. As long as y is not 0, which we just assume it's a positive whatever variable, y to the 0 is 1. And that's it. So anytime you see that exists in your things and I cross it out, like this one, number 15. When you see me write out number 15, 9x to the 0, y to the negative 3rd, you'll see me deal with this x is 0 and say, I'll say that's 1. And my crossing out is a way of saying it's not visible because 9 times 1 is just 9. So, you know, I don't need even to write a 1 there anymore. So now I have 9 times y to the negative 3rd, and y to the negative 3rd can now go down into the denominator and become y to the positive 3rd power, like that. Now the 9 won't go with it, right? This is 9 times y to the negative 3rd power. This doesn't go down with it, unless, you know, in the denominator, unless it was in parentheses, and if it was in parentheses, then you would have raised 9 to the 3rd power as well while you were doing it. So we're just finished there. Number 16, we have 15 c to the negative 8th times d to the 0 power. As you know, d to the 0 is 1. And once again, the 15 will not go down with the c as we turn the 8, the negative 8, to a positive 8. This will become 15 over c to the 8th. Number 17, 2 to the negative 2nd power times m to the negative 3rd power over n to the 0 power. N to the 0 is 1. Both 2 to the negative 2nd and m to the negative 3rd will go down because they are bases each with their own respective negative exponent. That doesn't mean there isn't anything on the top. There is still a 1 on the top. So don't ignore the fraction and just say, oh, it went down, but there's no more fraction. It's now 1 over 2 squared is 4, and m cubed is, yes, m cubed. Number 18, 10 to the 0. See, if you're tested on these, you'll probably only get a to the 0 power thing once on a problem instead of all the time. I don't know if that's true. But because we're practicing it, they want you to know it on every front. 10 to the 0 power is 1. R to the negative 11th power in the numerator becomes r to the positive 11th in the denominator. And s will remain atop, and 3 squared is 9. So I will just have s on top. That's not a 5. 3 squared is 9 times r to the positive 11th, like so. Number 19. See, they go relatively quickly. You have 4 to the negative 3rd times a to the 0 over b to the negative 7th. A to the 0 power is 1. 4 to the negative 3rd goes in the denominator as 4 to the positive 3rd. B to the negative 7th goes in the numerator as b to the positive 7th. And 4 cubed is 64. So you get b to the 7th over 64. Number 20. P to the negative 8th over 7 to the negative 2nd times q to the negative 9th. Each of them have their own negative exponent to deal with. So we will be moving this guy up, this guy up, this guy down. And you now have 7 to the 2nd, q to the 9th, and over p to the 8th. 7 squared is 49. And this is q to the 9th over p to the 8th. So the first set that we're testing is really just with the negative and 0 exponent. Later, after that, we should be doing the product of powers and, all that kind of stuff, maybe within having negatives. 21, 2 squared times y to the negative 6th over 8 to the negative 1st times z to the 0 times x to the negative 7th. 2 squared will be 4. 8 to the negative 1st will come up and become 8 to the positive 1st, which is just 8. That will multiply with the 4. The z to the 0 is 1. y to the negative 6 will go down to become y to the positive 6. X to the negative 7th will come up to become x to the positive 7th. So times x to the positive 7th over, looks like we're now just left with y to the 6 down below. So as long as you can organize your own work on it, you should be okay. 4 times 8 is 32. No more z's. There never were any, right? And lastly, number 22. 13 x to the negative 5th y to the 0 over 5 to the negative 3rd z to the negative 10th. Now, I will use this one as an opportunity to do things a little more in my head, because down the line you'll probably see me do that more where I'm able to exercise that, which is, I mean, I don't know, I'll still draw little arrows here, go up, down, and cancel, and go up. Most of it's in my head anyway. So 13 is still up there. 5 cubed comes on up. Z to the 10th comes on up, and x to the 5th goes down below. You still have to do 13 times 5 cubed. 13 times 125. Let's see. 125 times 10 is 1250, plus another 375 is 1625, I think. Check me on that. 1250 plus, I think 1625. All right. Okay, and that should be taken care of. So that's that set, and now we're going to start doing more with the other properties. This is a quotient of powers that I see here, for example. So number 23, we have 5 to the 6th over 5 squared. Now, as I said in the notes portion, the way I'll be doing this is I'll say we'll divide out the 2 5s down below and 2 of the 5s up top, or we'll get rid of, and we'll be left with 4 of them. So now we're left with 5 to the 4th up top, which is 625. Number 24, once again a division. With, oh, by the way, these need to have the same base when you're doing this. Negative 6 to the 8th over negative 6 to the 5th equals, we remove all 5 negative 6's down below and 5 of the negative 6's above, so you're left with negative 6 cubed, quantity cubed, which is negative 216. Number 25. Negative 9 squared times negative 9 squared. Now you could turn this into 81 times 81 and go off that. There's no problem with that. Likewise, you can also add those exponents, get negative 9 to the 4th, and now do that same process. Use your calculator. I don't actually know this. I could use my calculator. So let me show you what calculator I'm going to use, because I get to use it for the first time. Negative 9 to the 4th. I was trying to guess. 6561. I've seen that number before. I just didn't have it in place here. All right, 6,561. Number 26. Okay. There are a couple ways you can see this one. I'll show you both of them. And that's kind of one of the ways that can make some of these overview videos, these problem set ones, go longer when I say there's more than one way to do it. For the sake of, this is our first time seeing it, this is what I'm going to show you. You could either see that with the same base, that you can add these two exponents together, 4 to the negative 5 plus 5, which is 4 to the 0, which is 1. Or you could take this negative exponent here, become 1 over 4 to the 5th, and then it becomes 4 to the 5th over 4 to the 5th, and anything divided by itself is 1, or you get to subtract these exponents and you get to the 0, which is still 1. But that's one of the reasons why 0 to the 0 power isn't 1, because imagine that would then be 0 to this times 0 to this, which is 1 over 0 to the 5th. 0 to the 5th is 0. You can't divide by 0. So that's kind of one of the reasons why that's a problem within if we saw it that way. All right, number 27. P to the 6th to the fourth power. This is that power of a power scenario. The exponents multiply. 6 times 4 is 24. Number 28, that's an s. We have s to the negative 5 cubed. You'll multiply these. You get s to the negative 15th. Oh, my 5 looks like an s. S looks like a 5, whatever. We're not done, though. We have to get a positive exponent. That's 1 over s to the 15th. Hopefully that looks more like a 5. Or that looks more like an s. I'm not really sure. Number 29. This is that same kind of concept as I mentioned on number 26. You can do either way. Here's my general, not rule, but my general way of how I tend to go about these, like I stated, is I am comfortable dealing with negative exponents within the problem unless it's a fraction, in which case I like to get rid of them as soon as possible. Here, I tend to add these first and get 6 to the negative third, and then deal with the thing. That's just something in my mind. I don't create a fraction until it's necessary. If a fraction's already there, then I like to take care of it within. And there are reasons I like to do that other way, especially move things up and down, because you don't want to accidentally subtract a negative and not add correctly or something like that. So there's something big with that. Anyway, this becomes 1 over 216. No matter which way you do it, you should still get that answer. Number 30. Oh, okay. We have negative 7 times this negative 7 in a quantity raised to the fourth. Now, you can't multiply these negative 7s straight up because the order of operations here. And you might say, this one's in parentheses, this one's not. Is it different? Not really. You have to understand that this negative 7 is really negative 7 to the first power. And that's what's happening. So we have negative 7 to the first times negative 7 to the fourth, which means we kind of keep those negative 7s. And we add the 1 and 4 to get 5, negative 7 to the fifth power. And let me just see what that is. Negative 7 to the fifth gives us negative 16,807. Okay. Number 31, x to the fifth over x to the fourth times x. One of those more than one way to do it things. Either divide these first, which means you subtract the exponents. All 4 x's go down here, and only one's left up here. So you're left with x to the first times x. And once again, make no mistake, that does mean x to the first as well. X times x is x squared. It's x squared. The other way you can do it is this x. It's really x over 1, right? This x is a numerator value, meaning we could have multiplied these two first. That is still x to the first, and x to the fifth times x to the first is x to the sixth. X to the sixth divided by x to the fourth would leave you with x squared as a result. Number 32, z, because this is kind of what I'm going to be doing this problem, right? I'm going to multiply these on the top because they appear in the numerator to begin with, so it's just more commonplace to do that. So instead of subtracting these two first, let's just take care of these and add those two first. Z to the 10th over z to the 5th becomes not z squared, but z to the 5th. Remember, 5 pairs of z's are removed on top and bottom. You're left with 5 z's on top in the numerator, z to the 5th. Okay, let's move forward to number 33. Using properties. A microscope magnifies an object 10 to the 5th times. 100,000 times? 100,000 times. The length of an object is 10 to the negative 7th of a meter. What is its magnified length? So the original object is 10 to the negative 7th large in like reality to the naked eye. Then we magnify it this many times larger. And now we want to see how it appears to us. So negative 7 plus 5 is negative 2. It becomes 10 to the negative 2 meters. That is one version of an answer. Although we have also seen that they don't like negative exponents. Why'd they give them to us? I don't know. Let's just deal with it either way. That's 1 over 10 squared meters, which is 1/100th of a meter, or 0.1 0.01 meters, which is 1 centimeter. So any of these answers look pretty good to me. I think that's a centimeter, right? 100 centimeters is a meter. So I think that works to me. Its magnified length is 1 centimeter. That's the way I like to see that one. Number 34. Using properties, the area of the rectangular computer chip is 112 a cubed b squared square microns. What is the length? So the width is 8 AB microns. So we have a computer chip here, with 8 AB microns in width, an unknown length, which we're trying to solve, and the whole area is 112 a cubed b squared microns. The area of a rectangle is its length times its width. So length times width. Let me do it the other way. I like my 8 first, OCD. Width times length equals area. To solve for length, we have to divide both sides by its width, like so. This all becomes 1. It's gone. You're left with L. So L equals 112 a cubed b squared over 8ab. Our goal is to now simplify what's here. 112 over 8. I don't see that often, but let's see. I think it's 14. 80, 32. It's 14. So there, you're left with 14 in the numerator. A cubed over A, that A is gone, and A is gone from here. You're left with 2 of them. This B is gone. You're left with just 1 B here. So you're left with A squared B. That is the, let's see, square microns. Square microns. This is the length. This is the length of the computer chip. A rectangular computer chip. As we divided area by width. Number 35 and 36, error analysis. Describe and correct the error in simplifying the expression. All right, let's just take a look at them. And then we'll describe them. 2 to the 4th over 2 to the 5th. So they ended up multiplying the 2's as they added the 4 and the 5. They should add the 4 and the 5, but they shouldn't multiply the 2's. So let's state that, and then we'll correct it. So number 35, the 2's in the bases were multiplied to become 4 when they should have remained 2. Now that's my explanation for what was wrong. The reason for that, once again, is because when you add the exponents describe how many of those 2's will ultimately be multiplied. When you get 2 to the 9th as an answer, which is how we correct it, right? When we get 2 to the 9th as an answer, that means 2 times 2 times 2 times 2 times whatever. Those 2's will be multiplied. So 2 to the 4th times 2 to the 5th. Don't multiply these 2's now. The 9 is describing all those 2's that will be multiplied after. 2 times 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 2. I hope I said 9 of them, which is 512, to my knowledge. Instead of 4 to the 9th, which is now 9 4's being multiplied, and that's not what we're doing. And then number 36, x to the 5th times x cubed over x to the 4th equals x to the 8 over the x to the 4th. They added the 5 and 3, so far so good. Equals x to the 8 divided by 4, which is incorrect, which is x squared. So 8 divided by 4 is 2, but you are not dividing the exponents. You're dividing the x's, right? So 36, they divided the exponents in the quotient of x's when they should have subtracted them. I'm not going to get deep into the why. That was during the lecture. What I will just state as a reminder for you guys is that, once again, you are not, this is division indeed, but you are not dividing 8 and 4. You are dividing x to the 8th and x to the 4th, right? That results in subtraction of exponents, and you get x to the 4th as an answer. So that's just a reminder. And the reason why I also remind of this is because you will learn and understand, for the most part, whenever I have my students and stuff like that, you will learn and understand these properties, and you'll learn to subtract exponents and all that. What I want to refrain you from doing is later have 8 divided by 4 somewhere, and then turn it into 4. No, that doesn't happen. Division doesn't mean subtraction. Division of bases with exponents means you subtract the exponents. And they have to be the same base, by the way. You have to be the same base, otherwise there's no consolidation of how many are being multiplied. Okay. Moving forward to numbers 37 to 44. Some things with parentheses. Oh, that's multiple choice. Okay. Simplify the expression. Write your answer using only positive exponents. Number 37, we have the quantity negative 5z raised to the third power. This is where both the negative 5 and the z separately get raised to the third power. I'm going to keep the negative 5 in exponent in parentheses, though, because the 5 is negative, and then the z being cubed. Negative 5 cubed is negative 125, and z cubed is, yes, that's the result. Number 38, 4x to the negative fourth power. Now, you could do this one of two ways. You can either apply the negative 4 first to both of these, like raise to the negative fourth, or treat this negative 4 immediately, like 1 over 4x to the fourth, turn it positive like that. Doesn't matter either or. I'm going to give you this one this time. You get 4 to the fourth and x to the fourth here. 4 to the fourth is 256. And you get x to the fourth there. Number 39. 6 over n to the negative second power. This is one of those instances where I will take care of the negative exponent first. And I'll turn it into n over 6 to the positive second power. Basically, both of the inside parts, which would have gotten negative exponents, I switched numerator and denominator as a result of turning the exponent positive, as we kind of need it to be. N squared over 36 is your result. Number 40, negative t, 40, you have negative t over 3 squared, which means we will square the negative t, and we will square the 3. I'm thinking of whether it's worth saying this part here. Like negative t is negative 1 times t, and then you'd be squaring the negative 1 and the t separately. I don't know. So anyway, negative t squared is positive t squared, and then 3 squared is 9. So you get t squared over 9. Number 41. 3s to the 8th. I wish they didn't use s's in the same problem where they used 5s. To the negative 5th. You see the problem? The 3, this time I will, from here on out, I'll try and keep negative exponents whenever it's a non-fraction problem until I don't need to. So 3 to the negative 5th times s to the 8th to the negative 5th. You have to make sure you know what are s's and what are not, because I just have trouble with that. It's one of my many vices. So now that's 1 over 3 to the 5th times 1 over s to the 40th. 8 times 5. Right? I treated them positive, you know what I mean. 3 to the 5th is 243. So 1 over 243 s to the 40th. Number 42. Negative 5p cubed. Remember to cube the negative 5 as well as the p cubed. Now negative 5 cubed is negative 125. P cubed, you multiply the 3's and you get p to the 9th. Number 43. Negative w cubed over 6 to the negative second power. Let's treat the negative exponent positive and flip this fraction. Negative 6 over w cubed to the positive second power. As we square this whole thing, you might ask where the negative goes to. Does the negative go to both the numerator and denominator? Does it just go to one? Does it apply the fraction? Ultimately, we're going to square it anyway, so that part shouldn't matter. But it only applies to one part of it. is -1 times the whole thing. Make it with the 6 or the w. But ultimately, this will become positive something. So I'm going to square the 6, and I will get 36. I'm going to square w cubed, and I will get w to the 6th power. Remember, we are squaring w cubed. We are not squaring 3. And that's just the cleanup of that. And lastly, number 44, at least for this section, or this portion, 1 over 2r to the 6th to the -6th power. Flip the fraction. 2r to the 6th over 1 is just 2r to the 6th. And now this 6 is positive. Now I get to raise 2 to the 6th power and r to the 6th to the 6th power. 2 to the 6th is 64. R to the 6th to the 6th is r to the 36th power as you multiply them. Okay, number 45. Whoops, let's go back. I'm sorry. Number 45, using properties. Which of the expressions represents the volume of the sphere? Explain. Okay, this is one of those instances where they don't tell us the formula for the volume of a sphere. I will happily tell you that to lead you into what it is that we're doing. The volume of a sphere is 4/3 pi r cubed, where r is the radius of the sphere. This sphere has a radius of 2s squared. So which of the ones, I don't know if this is just one answer or many, I assume it's just one of them, is something that represents the radius. And I'm going to simplify it and get to the answer and see if that matches, but it might not be the only answer that's here. They give you different ones, and I'm not a fan of that because I can't guarantee that some of these other ones aren't necessarily true. I'll go through all of them and see which does and doesn't work. So let's take a look. So our volume, we're going to substitute 2s squared in for r. So 4/3 pi times 2s squared cubed. That's r cubed. So let's go ahead and simplify that portion. This, like I said, this may be one of the answers that's on this option set. I don't know yet. So that's 4/3 pi times 2 cubed, which is 8, times s squared cubed, which is s to the 6th. If I were to attempt my own cleanup without looking at the multiple choice options, 4 times 8 is 32. Do they put pi's or s's first? I think pi. Times s to the 6th all over 3. So this is my version of the answer I would go for. Are there units? No. So let's see if this answer's on there. And then we'll see if there are other ways that we can have that rewritten and correct. So C looks to match that exactly. So my answer is C, and I believe it's multiple choice, not multiple selection. To overrule some of these, it's definitely not, well, not definitely not. Whew, well, it was close to A. Okay, I'm just going to guess it's only one answer here. Oh, no. I'm looking at D. D may be correct as well. D may be correct as well. Okay, then let's look through these. A. Okay, here's how I'm going to do this. I'm going to go through the multiple choice options now that aren't simplified, and I'll simplify them as better practice and see if it can line up with this. This one gets close, actually. It just misses the boat, I think, with the 32. Everything else seems pretty close. And this is one of the kinds of, these are some of the kinds of problems I like to do more anyway for these. Okay, so with that negative first, you've heard me say it before, I like to turn it positive, blah, 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 and I will. But sometimes I like to simplify what's inside of here when I can so that I have less to flip around and do later, such as s squared over s to the 8th, get rid of the 2 s's here, and 2 of them here to be left with 6 of them. And 2 to the 4th will be 16. So now this will say 3 over 16 pi s to the 6th raised to the negative first power. Now when you turn the negative first into a positive first power by flipping this fraction, you get 16 pi s to the 6th over 3. That's pretty close to this. The difference is that's 32, that's 16. So it's not A. I think D is an answer, though, so we'll take a look and see what else may be. Oh, and it looks like B might be as well. So B, we have 2 to the 5th pi s to the 6th times 3 to the negative 1st. And really all I have to do is just take care of 3 to the negative 1st goes down to 3 to the positive 1st, and 2 to the 5th is 32. So you get 32 times pi s to the 6th over 3. So A was a no-go. B is a yes-go. B does work. So B is correct. So we do have B. We already saw C, which is the most simplified of them. D, 2s all to the 5th times pi s over 3. 2 to the 5th is 32. S to the 5th is here times pi s over 3. Remember, this is a product, so that over 3, everything's really over 3 here. S to the 5th times s to the 1st is s to the 6th. So 32, and I'll write the pi first, and s to the 6th all over 3. D is also correct. So I'm glad I didn't just move on and say it was only C. Let me debunk E automatically here on this one. If we are going to bring this down and this up, yes, 32 goes up and 3 goes down, but pi and s to the 6th go down with it, so it can't be E. And F has s to the 5th instead of s to the 6th, so because of that part, otherwise it would be correct, it's not F. So B, C, and D. B, C, and D. Okay, cool. I'm glad we got to do some of those other ones, actually. All right, number 46, modeling with mathematics. Diffusion. Wait, is that the word in... I'm thinking of Oppenheimer. What are the two words that they... Fusion and fission. I was thinking of that. Let me drink water while I think on that a little bit. Okay. Number 46. Diffusion is the movement of molecules from one location to... It sounds like Oppenheimer. From one location to another. The time t in seconds it takes molecules to diffuse a distance of x centimeters is given by t equals x squared over 2d, where d is the diffusion coefficient. The diffusion coefficient for a drop of ink in water is about 10 to the negative 5th square centimeters per second. So, hold on, 46. We have t equals x squared over 2d. And d in this case for ink in water is 10 to the negative 5th square centimeters. Okay. How long will it take the ink to diffuse 1 micrometer, which is 10 to the negative 4th centimeters? So I think we're substituting 10 to the negative 4th for x. If x is the distance of diffusion that we're diffusing something, the number of centimeters that we are, x, we're going to be using 10 to the negative 4th. That's what I believe this is. I apologize if that's not correct. I think they're giving us real life application. They're telling us what it would be in these cases, and we go to town with it. So the time it's going to take, and this is in seconds, time in seconds, we are going to take our 10 to the negative 4th distance that this ink will go in water. We're going to take the diffusion coefficient for ink in water, and we'll see how long it'll take for it to diffuse them molecules. So 10 to the negative 4th squared becomes 10 to the negative 8th as you multiply negative 4 and 2. The 2 does not multiply with this 10 because 10 is being raised to the negative 5th power first, but it is in the denominator here even still. What I'm first going to do is take care of these 10s in such a way. Let's just turn them positive first. And this is where, again, to avoid confusion, you don't want to do negative 8 minus negative 5. Forget that you have to subtract the negative instead of just subtract. Have a negative exponent, not sure whether to put it in numerator and denominator. It becomes a hassle. It becomes a hassle, and it's better solved if you just place them where they're supposed to be when you have a fraction, when they're positive exponents. This alleviates a lot of issues for me. All 5 10s go away in the numerator. You are still left with 1 on top, right? And 5 of them get removed in the denominator. You're still left with 3 of them. So now we have time as 1 over 2 times 10 cubed. This is in seconds. So 1 over 2 times 1,000, which is 1 over 2,000, or 1/2000th of a second. It doesn't take long. It doesn't take long. I hope I got that, like that you're substituting and stuff correct. All right. Oh, these are the kinds. Okay, so these are the kinds of problems that I won't say enjoy most, but these are the ones that they kind of cover it all. These are the ones that you're supposed to make sense of the information with. So perfect. Okay. This is where my students understand what to do. In 47 to 50, simplify the expression, write your answer using only positive exponents. And this is where it's one of those, there's more than one way to do these. I'm mostly just going to try and affix myself to the one way that I would personally prefer doing them. I might give you more markings than I generally do in my head, but otherwise this is exactly where we're intending to go with these kinds of problems. Okay, so as an example, which I'm not going to do, this 4 can apply to every portion of this product, this, and this, and work it out. But I'd rather simplify what's inside first before doing the 4th power thing. Meaning, let's first turn negative exponents positive, like so. So we'll first get 2y cubed times y to the 4th over 3 times x squared, all raised to the 4th. Now, y cubed times y to the 4th is y to the 7th. X times x squared is x cubed, and that's to the 4th. So now that we've cleaned up the inside, and 2/3 couldn't reduce, but I would have done that too. Now that I've cleaned up the inside, now I'll raise these parts to the 4th power. So to the 4th power goes 2, y to the 7th, 3, and x cubed. So now we're going to have 2 to the 4th. Y here. Okay, this is the only time that, unless it's really hard math, I'm going to write these parts out. At this stage, we're at the stage where we've seen these enough, and I think we got to know what we're supposed to do with them. 2 to the 4th is 16. This becomes y to the 28th. This becomes 81. And this becomes x to the 12th. So next time, I'll just go straight probably from this step to this step, saying out loud 2 to the 4th is and stuff like that. Okay. Number 48. And all these are pretty much the same biz with how I talked about let's simplify what's inside first as long as we are able to. So inside I have 4s to the 5th. Thank you for using s's and 5s right next to each other. I very much appreciate that. Ultimate sarcasm, you know this. T to the negative, let's do that again. T to the negative 7th over negative 2 s to the negative 2nd times t to the 4th, all raised to the 3rd. Okay, without writing any marker stuff, I have 4 over negative 2, which is negative 2. That's in the numerator. S to the 5th is still on top here. I'm going to bring up s to the negative 2nd to be s to the positive 2nd up here. I will bring down the t to the negative 7th to become t to the positive 7th and multiply that by the t to the 4th. Remember, 4 over negative 2 already became negative 2, and that's in the numerator. Now, s to the 5th times s squared is s to the 7th, and t to the 7th times t to the 4th is t to the 11th cubed. Negative 2 cubed is negative 8. S to the 7th cubed is s to the 21st, and t to the 11th cubed is t to the 33rd. And that should be a result. Okay, numbers 49 and 50, you see 2 different parentheses, quantities raised with exponents and all that. You can't intermingle those 2 quantities, even though they're separated by product, because they have the exponents first. So this time you will have to do some simplification before you move some bits over. So just be ready for that. Number 49, 3m to the negative 5th times n squared over 4m to the negative 2nd times n to the 0. See how we haven't seen to the 0 power in a while? That's what I'm more familiar with. So it's not like they show up everywhere. And this is one of those like, oh yeah, just a little reminder that it's there. Okay. Within this individual quantity, n to the 0 is 1. Let's just, like, basically just get rid of it. It's just basically not there. I'm going to be bringing, I'm going to switch those places. So this guy down, this guy up. And in this quantity, n to the fourth over n is n cubed, like that. So now as a rewrite, it'll look like 3, m goes before n alphabetically, right? M squared n squared over 4 m to the fifth. And this is m n cubed over 9 squared. So I'll kind of do this in like the one-step part. I have to still treat these m's here. Get rid of the 2 up here and the 2 of them down here with, now we have m cubed. Now let's start squaring both of these parts separately. 3 squared is 9. N squared squared is n to the fourth. 4 squared is 16. And m cubed squared is m to the sixth. M squared n to the sixth over 9 squared, which is 81. Now that it is a product of two fractions, it's technically this times this over that times that. Basically, anything here is dividing by anything here as well, and vice versa. For instance, I have 9 over 81 right here. 9 over 81 is 1/9. I can reduce that. M squared over m to the sixth, get rid of the 2 m's here and 2 m's here, and you're left with m to the fourth. And I think that's all we can, oh, and then n to the fourth times n to the sixth will fuse together. So now on top, we just have n to the 10th, 4 plus 6. And down here we have 16 times 9, which is I think 144. Yeah, 144 and m to the fourth. There we go. And lastly, number 50. What time are we at so far? 1:06. Number 50. 3x cubed, y to the 0, over x to the negative second to the fourth times y squared x to the negative fourth over. Okay. All right, one part at a time. Y to the 0 is 1. I'm going to bring this guy up. That'll become x squared, and that'll end up multiplying with x cubed. So in the first quantity, we will have 3x to the fifth power raised to the fourth. Those exponents will add together. In the second one, this guy will go down. This guy will go up. Y squared will multiply with y to the 8th. You'll get y to the 10th. In the denominator, you still have a 5. And x will multiply with x to the 4th to get x to the 5th. And that's all raised to the third power. 3 to the 4th is 81. X to the 5th to the 4th is x to the 20th. Y to the 10th cubed is y to the 30th. 5 cubed is 125. X to the 5th cubed is x to the 15th. Now remember, this is all part of that same fraction. 81 over 125 cannot reduce. X to the 20th over x to the 15th can. And here you'll get x to the 5th on top with no more x's down below. So now you have 81, x to the 5th, y to the 30th, all over 125. And that is simplified. Okay, now we move on to numbers 51 to 54 with scientific notation. There were some examples that were provided earlier on, like to show, indicate what we're going to do. Basically, treat the numbers in front with each other where you can, and then the tens raised to certain exponents treat together, and then see if we have to clean anything up after. So evaluate the expression, write in scientific notation and standard form. If standard form means evaluate it, then I guess, okay, we'll do that. Like with a fraction. 3 times 10 squared times 1.5 times 10 to the negative fifth. So what we're going to do is we're going to multiply the 3 with the 1.5. And that'll be times, and then we're going to have 10 squared. Whoops. That's all right. 10 squared times 10 to the negative fifth, like that. 3 times 1.5 is 4.5. And 10 squared times 10 to the negative fifth becomes 10 to the negative third. There's a scientific notation answer. I don't know what they mean by standard form, if they actually mean, like, evaluate it. And if they do, then I'll go for it. This becomes 4.5 over 10 cubed, which is 4.5 over 1,000, which is 45 over 10,000. And I can definitely divide these by 5. That becomes 9 over 2,000. So if that's what they meant, great. There are some of these where I don't know if I'll be able to do it in my head like that, but there's one. Number 52. So I apologize if that's not standard form, by the way. I'm actually not bothering to look it up, but that looks good to me. Number 52. 6.1 times 10 to the negative third times 8 times 10 to the eighth. So if you, or 10 to the ninth. So if you understand what we are doing, I am going to multiply 6.1 with 8. I'll do it on the calculator here. 6.1 times 8. So, why didn't I knew that. 48.8. I was intimidated by the decimal and didn't realize. Okay. And then you add the exponents here. So I'm going to get 10 to the sixth. So there's one version. This is not yet scientific notation, though, because scientific notation is more about just the ones place. So if I move this thing over to make the number 10 times smaller, then I have to make this portion 10 times larger, which means I have to increase the exponent by 1. So this will become 4.88 times 10 to the 7th power. So that's the proper scientific notation version that they'd want. Now the actual value would be 4.88 times, I guess, 10 million, which I guess becomes 48,800,000. Whoops. 800,000. Yeah. I believe so. I hope I did the decimal stuff correctly. Number 53, division 6.4 times 10 to the 7th over 1.6 times 10 to the 5th. 6.4 over 1.6 stands out to me as 64 over 16, which is 4. So that's 4 times 10 squared. That's kind of scientific notation. I don't know if they need the decimal. 4.0 times 10 squared. Either or, you're pretty good. Now, 4 times 10 squared is 4 times 100, which is 400. So scientific standard. I hope that's standard. And then 54, 3.9 times 10 to the negative 5th over 7.8 times 10 to the negative 8th. It's one of those bits again where it's like, I want to like flip these just because, make it 10 to the 8th over 10 to the 5th. So 10 to the 8th over 10 to the 5th. Just keep that in mind. 3.9 over 7.8, 39 over 78. That's half, right? 1/2. So that's 0.5 as a decimal. So that's 0.5 times, it looks like that's 10 cubed now, right? Now we have to shift this decimal one place over to make it instead 5.0. So if I make this number 10 times larger, then I have to make the scientific notation part 10 times smaller, which means make it 10 squared instead. So 5.0 times 10 squared, which is 5 times 100, which is 500. Or S100. Okay. All right, number 55, problem solving. In 2012, on average, about 9.46 times 10 to the negative first pound of potatoes was produced for every 2.3 times 10 to the negative fifth acre harvested. How many pounds of potatoes on average were produced for each acre harvested? Write your answer in scientific notation and in standard form. So for every 1 acre harvest, so this is kind of a proportion-ish, if you will, if you understand where we are with it. Let me kind of say it in a different way. If you buy $8 worth of two apples, how much would it cost to buy, how much money would you spend for one apple? You have to turn it into the one. So the pounds of potatoes, so this is like pounds of potatoes per acre harvested is what we're doing as a ratio. We need to find out how many pounds of potatoes per 1 acre. So let's write out the division of this one, 9.46 times 10 to the negative first pounds of potatoes divided by 2.3 times 10 to the negative fifth acres. And as long as we do the division and get it, write it as a quotient with no fraction, then that's per 1 acre. Then that'll work out. That'll be fine. So that'll be pounds per acre. So let's just go ahead and do that division. Now, I don't know this division. This is one where I will use the calculator, and I have no reason to believe that I should know it. 9.46 divided by 2.3. That's a very strange number. I want to make sure that that was good enough. That many pounds of potatoes for every acre. How many pounds on average were produced for each acre? So the number, it's not great. We'll have to do a little bit of rounding if that's okay. This becomes 4.113-ish times, and once again, this is like if we swap those, 10 to the fifth over 10 to the first, that becomes 10 to the fourth pounds per acre. So that's scientific notation. Again, there was some rounding involved. Let me write a few more in case it's like important for the standard form, because 10 to the fourth is 10,000. So we'd have to move that 4 decimal places over. So we would get 41,130 pounds per acre. There. And that seems like a legit number. So yeah, I'll just go ahead and leave it as that then. I guess we don't have to do anything more with that. It's just I wish they would have given you a clean number in the division so you were trusting of the, they didn't ask us to round or not. And yeah, that's what we got. Okay. Number 56. Problem solving. The speed of light is approximately 3 times 10 to the fifth kilometers per second. Very fast. How long does it take sunlight to reach Jupiter? Write your answer in scientific notation and in standard form. Well, it would be nice to know how far... Oh, there it is. I was like, it'd be nice to know how far the sun is from Jupiter. Okay, so the average distance from the sun to Jupiter is 7.8 times 10 to the 8th kilometers. I remember really quickly, I was doing a SAT prep with somebody, and we didn't look at one page where they were showing the data of a falcon's speed for something like that, and then they're like, when will the falcon like hit the water and stuff like that. We're sitting there going like, is this supposed to be like obvious information to somebody? I don't really know, but it wasn't. And then we finally said like, oh, we totally skipped that page. Okay, speed of light is 3 times 10 to the fifth kilometers per second. How long does it take sunlight to reach Jupiter? So that's speed, and then we have distance. So if you know, distance is, rate is distance over, so distance is rate times time. And we have distance as 7.8 times 10 to the 8th. We know the rate, 3.0, if you will, times 10 to the 5th, and we need to solve for t. So like that. I guess I don't need parentheses here. So to solve for t, we will divide distance by rate. So the time will be 7.8 times 10 to the 8th divided by 3.0 times 10 to the 5th. That should reduce because 78 over 3 is 26, so this should be 2.6? I don't trust myself. 7.8 divided by 3. 2.6, okay. Times 10 cubed. So that's the answer in scientific notation. This is in seconds. Now that's not 2.6 seconds. That is, and it's actually not that slow, I guess. It's 2,600 seconds, which is less than an hour. Cool. Yeah. I didn't know that. It takes that long for sunlight to reach Jupiter. All right, number 57. consider cube A and cube B. I have considered them indeed. Which property of exponents should you use? Oh, part A. Which property of exponents should you use to simplify an expression for the volume of each cube? So they give you, so a cube has all equal edge lengths. The faces are congruent. There's 6 of them and all equal edge lengths. So when you find the volume of a cube, you multiply the length, width, and height. It's, they say, side cubed or whatever. So when you find the volume of a cube, it's any of the sides raised to the 3rd power. So when we're doing like the volume of cube A, it would be 2x to the 3rd power, and the volume of cube B is 6x to the 3rd power. So when they ask you which property of exponents should you use, you end up doing the power of a product. Is that how you say it? The power, you use the power of product property. They don't ask us to explain, so I won't, but that's what you do based on a cube there. Now, they didn't ask us to simplify this, but I shall. That becomes 8x cubed and 216x cubed. B, how can you use the power of a quotient property to find out how many times greater the volume of cube B is than the volume of cube A? Now, let me just ask you this first, or state out loud. Although cube B is 3 times longer and therefore wider and therefore taller than cube A, it is not 3 times larger in volume. How many cube A's can fit inside cube B? You can bet there are more than just 3 that can fit inside there, because there are 3 dimensions to consider. It's not just 3 times the length, but also 3 times the width, whatever, and 3 times the height. So you can, 27 of them will fit in here. So how can you use that power of a quotient? How many times greater? You say, how many times greater is the length of cube B over cube A? You take this over this and you cube that, right? Because that's what gives you your 6x cubed over 2x cubed, which is the volume of one divided by the volume of the other, which is 216x cubed over 8x cubed. X cubed over x cubed is 1, and you're left with 216 over 8, which, by the way, can simplify because 6 over 2 could have simplified. So this becomes 27. 27. B, cube B, is 27 times larger than cube A. The concept involved in this, the 6x over 2x equals 3. Again, each dimension is 3 times longer, wider, taller. And then you cube your ratio of lengths to compare the volumes. You would square the ratio of lengths to compare the areas, in which case the facing of any side on cube B is 9 times larger than the facing of the cubing on side A. This is the facing of any one of side A, and there are 9 of them. 1, 2, 3, 4, 6, 7, 8, because of 2 dimensions. Okay. Because that's a bigger conversation in geometry to have. I guess this isn't really a geometry topic, though. Number 58, problem solving. A byte is a unit used to measure a computer's memory. The table shows the number of bytes and several units of measure. So a kilobyte has 2 to the 10th bytes, a megabyte has 2 to the 20th bytes, gigabyte 2 to the 30th, terabyte 2 to the 40th. How many kilobytes are in 1 terabyte? So number of it says, like, if you take a kilobyte's size and multiply it by this many times to get a terabyte, how many of them will it take? So that's why you have to divide by 2 to the 10th, like that. So how many does it take? 2 to the 40th over 2 to the 10th is 2 to the 30th. I'm not going to evaluate that, but how many kilobytes? There are 2 to the 30th kilobytes in 1 terabyte. I think terabyte is capital T. I don't know if the B like that, right? I don't know. Um, that's sad. I was a computer science major. B, how many megabytes are in 16 gigabytes? So I think it's best to just keep doing the algebraic version just so you're not kind of confused on where something goes. We want to know if you take a megabyte, 2 to the 20th, and multiply it by a certain amount to get 16 of these gigabytes, like that, then you can solve for x that way as well, right? So 16 gigabytes divided by 1 megabyte equals the number of megabytes that are needed. Sorry, the size of a megabyte equals the number of megabytes needed in order to do it. So that'll be 16 times 2 to the 10th. I feel like that's something I'm supposed to evaluate a little more. See, 2 to the 30th wouldn't even really fit. Oh, no, wait, 2 to the 30th would probably fit. Hold on. Let me see what 2 to the 30th is. Oh, 2 to the 30th kind of fits. So let me rewrite a little bit. It's a large number, but 10737418824. I just thought it wouldn't fit in that. This one should fit, though. So 2 to the 10th is 1,024. 16 times that 1,024 is 16384. So 16,384 megabytes in 16 gigabytes. Part C, another unit used to measure a computer's memory is a bit. That's right. That's right. There are 8 bits in a byte. How can you convert the number of bytes in each unit of measure given in the table to bits? Can you still use a base of 2? Explain. So, if there are 8 bits in a byte, then these sizes will each become 8 times larger. Okay, so if I made this table, unit number of bits, this time a kilobyte will have 8 times 2 to the 10th. Megabyte will have 8 times 2 to the 20th. Gigabyte will have 8 times 2 to the 30th. And terabyte will have 8 times 2 to the 40th. Okay, they ask you, though, can you still use a base of 2? Yes, because 8 is 2 cubed. So what we can do instead is turn this into 2 cubed times 2 to the 10th. 2 cubed times 2 to the 10th, and that's 2 to the 13th power. You basically add 3 to that number. You'll do the same thing here. This becomes 2 to the 23rd. This becomes 2 to the 33rd. And this becomes 2 to the 43rd. So you multiply 8, which is 2 cubed, into that, and you add the 3 with it. That's a real-life application. That actually works there. I mean, I'm not surprised, but I'm just kind of going like, yeah, that's what we do. All right, this is the last set of frames here. So 59 to 62, rewrite the expression as a power of a product. So I guess we're going backwards now. So 59, we have 8a cubed, b cubed. So power of a product means we need to get this raised to a power. Because these are cubed here and 8 is a cube, we can cube 2ab. So like that. This is what it could have been before we simplified it. So there's just some backwards thinking to be had. You have to recognize what's there and what you can do with it. That's basically how well do you know your values. I don't know how much work I can really show on this from you guys other than to say out loud what I'm thinking on it. Next one, 16r squared s squared. Hey, there's no 5. Good. They're both squared, and 16 is a perfect square of 4. So this can be 4 times r times s, quantity squared. 61. 64 times w to the 18th times z to the 12th. Now, there's more than one answer to this, as in 64 is a perfect square, but it's also a perfect cube. It's also a perfect sixth power value. So there's more than one answer to these, as 18 and 12 can divide by 2, 3, and 6. I will do the largest one. I will say out loud the other ones, though. 64 is 2 to the 6th power. W to the 18th can divide, 18 can divide by 6 and get W cubed, and 12 can divide by 6 to get 2, and those can all be raised to the 6th. That is the simplest form of it. If you did, say, something squared, this would be 8, W to the 9th and Z to the 6th, and something cubed would be 4 times W to the 6th and Z to the 4th, as you take the cube root and divide these by 3. Lastly, 62. So my aim is to make it as small as possible, because that's what I like. It's kind of like a greatest common factor. 81, same thing on this one. 81 x to the 4th, y to the 8th. You can either take square roots of everything here or fourth roots. If I can go fourth root here, 3 to the 4th is 81, and x to the 4th would give you that, and y squared to the 4th would give you y to the 8th. And that's my preferred go-to instead of 9 x squared y to the 4th quantity squared. Okay, 63. Using structure, the probability of rolling a 6 on a number cube is 1/6. The probability of rolling a 6 twice in a row is 1/6 squared, which is 1/36. So you're taking, a sixth of a sixth, because you got to do it successfully twice, right? Write an expression that represents the probability of rolling a 6 n times in a row. So if one time is 1/6 to the first, and twice in a row is 1/6 squared, n times is 1/6 to the nth power. That is part A. Part B. What is the probability of rolling a 6 4 times in a row? That's 1/6 to the 4th power, which is 1 to the 4th over 6 to the 4th. 1 to the 4th is 1, and 6 to the 4th is 1296, I think. Part C. What is the probability of flipping heads on a coin 5 times in a row? Explain. So a coin has heads or tails outcome. You have 1/2 chance of doing either. If we want to land heads successfully once, it's 1/2, twice, 1/2 squared, etc. 5 times in a row is 1/2 to the 5th power. My explanation is to you. Flipping a head has 50% chance, odds, and we have to do it 5 times in a row. That'll be 1/32. Okay. Number 64. How do you see it? The shaded part of figure N represents the portion of a piece of paper visible after folding the paper in half n times. Do I have paper for this? Sure, this is recycled. All right. So they're saying, whoops. Figure 1, you see this much paper. Figure 2, you see this much paper. All right, that makes sense. Okay. Etc. What fraction of the original piece of paper is each shaded part? Well, let's kind of make a table out of this one, because you see half of the paper in figure 1. So figure number and paper, portion of paper. Portion. Figure 1 has 1/2. Figure 2 has 1/4. Figure 3 has 1/8. Because you do a half of a quarter. And figure 4 must have 1/16, like that. So figure, I guess, N is, 1/2 raised to whatever power you're doing. The first, the second, the third, the fourth. However many halves you're going to do. So what fraction of the original piece of paper? Oh, okay, so I just answered that. I thought they were going to rewrite each fraction from part A in the form 2 to the x. So let's say it this way. Instead of figure x, not figure n, figure x is 1/2 to the x power. Now they said write it as 2 to the x power. So how do I turn 1/2 to the x power as 2 to the x power? Let's see how I say that. I mean, I know the answer, but we're not solving for x. We got to rewrite this. Okay, never mind. Okay, I said this wrong. Let's just do this. 1/2 is 2 to the negative first power. 1/4 is 1/2 squared, so 2 to the negative second power. 1/8 is 2 to the negative third power. And then, yeah, 1/16 is 2 to the negative 4th power. And that's 2 to the negative x, I guess you put it that way. But anyway, so here are those different forms there. Again, if you haven't noticed by now, and I've said it in each video, I sight read these. I haven't seen these before, so I'm trying to reason with it the best way possible. And I think that's probably one of the better things to do. So you see my mind as I work it out and think about how I want to say things. I'm trying to satisfy it in good time, but I don't know. Find x and y when b to the x over b to the y is 9 and b to the x times b squared over b to the 3y equals b to the 13th. And there's a part where I'm going to say I have no idea how to do it. So let's see. B to the x over b to the y equals b to the 9th. B to the x times b squared over b to the 3y equals b to the 13th. Okay, my attempt at doing this that I think I want to do is, because I have this expressed as b to the 9th here, I can either substitute this for b to the x over b to the y when I find it, or I can rewrite this with b to the x over b to the y equals. I probably want to do the former, which means I want to rewrite this so that instead of b to the 3y, it somehow says b to the x over b to the y. But there are 3 of them there, and I can't separate them fully. Let's see, what do they want? Find x and y. Because it does say b to the 3y, and I know how to rewrite that portion, but I want to just get a single b to the y there. Okay, I'll just do this instead. I'm going to solve for one of them, because I'm not evaluating. I just want to solve for one of these at a time. So let's multiply both sides of this by b to the y. Hold on, I'm trying to think if there's something else I want to do. Can I do that? Will that help? That won't help. Okay, I'm going to multiply both sides by b to the y power. And I have, so this is one of those where I'm not sure if I'm doing something well or not. And I'll have b to the 9th times b to the y. And I'm going to substitute this in for b to the x. Find x and y when. I mean, there's more, like, you can guess and check and get it right. Like now I'm realizing what I should have said. X has to be 9 more than y. Whatever x is, it has to be 9 more than y. Because when you're doing bx over b to the y, and that's kind of what this says, right? Because 9 plus, this becomes y plus 9. So b to the x is b to the y plus 9th power. That's fine. Not sure if that really helps me or not, though. So, okay, so anyway, let's see where we go with this. I'll substitute it for b to the x, because I want to use algebra, not guess and check. So I'll have b to the, I'll still do this, b to the y, b to the 9th times b to the y times b squared over b to the 3y equals b to the 13th. B to the 9th times b to the squared is b to the 11th. B to the y divided by b to the 3y. Now I do y minus 3y, which is negative 2y, or remove a y from here and remove a y from here and have 2 y's down here. So I have b to the 11th over b to the 2y equals b to the 13th. Okay. Now I'll multiply, I don't know how I want to best say it, but I'm going to multiply both sides by b to the 2y and divide both sides by b to the 13th. So I'll get b to the 2y equals b to the 11th over b to the 13th. B to the 2y equals 1 over b squared. So the y has to be, b to the 2y equals, here I'll just put b to the negative 2nd. So now that I have matching variable bases, I can set the exponents equal to each other. 2y is negative 2, so y is negative 1. Okay, as far as x goes, if you notice here, b to the x equals b to the y plus 9th, so x is y plus 9. X has to be 9 larger than y. So x is negative 1 plus 9, and x is 8. So it works out. There's way more than one way to do this. That's not guess and check. I mean, algebraically. It depends on what substitution you want to use and how you want to express it, and that was my go-to. That seems to work out. Some little instances, like you weren't necessarily sure what happened here. The idea is, these are both the same b, so I have to raise this to equal powers, right? So these have to be the same in order for that part to be equal. Same thing on this part here. Does that work? Is that a for sure? For sure. Let's try that. 8 minus -1 is 9. B to the 8th times b squared is b to the 10th. Divided by b to the -3rd. Yeah, b to the 13th. That works. Okay. 4 more problems. Thought-provoking, indeed. Write expressions for r and h so that the volume of the cone can be expressed by can be represented by the expression 27 pi x to the 8th. Find r and h. Okay, first things first, before I even really see what the problem's fully asking me to do, the volume of a cone is, remember the volume of a cylinder was pi r squared? I don't know if you saw the notes, the lecture. Pi r squared times height. Volume of a cone is 1/3 of that. So 1/3 pi r squared times height. Write an expression for r and h so the volume can be represented by the expression here. So if the volume is instead rewritten as 27 pi x to the 8th, let's set that equal to 1/3. Give me 1 second. Okay, let's set that equal to 1/3. What is this? Pi r squared, 1/3 pi r squared times height. So what do they want us to do? They say write expressions for r and h so the volume of the cone can be represented here. So now what we're going to do is get the radius in terms of this and the height in terms of this, I guess, as we're doing it. So now we want to solve for r and solve for h when we're doing it. So we want to get them by themselves. Because r and h, how do I say it best? There's no rhyme or reason to it. It's not like that the radius is half the height or anything like that necessarily. So we have to do them separately. So let's solve for r first. R. To solve for r, we have to divide both sides by 1/3 pi times h. Dividing by 1/3 is also multiplying by 3. Keep that in mind. 1/3 pi times h. So r. Now we're going to have r squared equals 27 divided by 1/3 is 27 times 3, which is 81. Pi over pi, and you have x to the 8th over h. You have to take the square root of both sides, and you get r equals the square root of 81 x to the 8th over h. Now, we are not currently in expressions for r and h, so the volume of the cone can be represented by the expression. I'm trying to think if there's something else I need to say with this. I don't think so. I don't think I'm missing anything on that. But we're not doing radicals yet, but when we simplify this, that would be 9x to the 4th over the square root of h. So I don't know. I hope I'm answering that one based on how it's kind of asking me to, although we haven't done things with radicals yet, but that's how I'm seeing it. The height, on the other hand, when we have that, 27 pi x to the 8th times equals 1/3 pi r squared times h. See, it would be one thing if they told us that the height was some many times larger than the radius or whatever, but they don't. So now let's solve for h by dividing both sides by 1/3 pi r squared. So gone, gone, gone. And here pi is gone. 27 over 1/3 is 81. And you have x to the 8th over r squared equals height. And that's kind of all we'd say with that. It says find r and h. I mean, that's what they are to me. I don't write expressions for r and h so the volume of the cone can be expressed by the expression here. Maybe I'm not answering that one based on how they're asking. Maybe it's open-ended. But that's how I'm solving for it with x involved. Unless they're asking me to do something else, that's what I'm going with. I apologize if I misinterpreted the problem. Number 67, making an argument. One of the smallest plant seeds comes from an orchid, and one of the largest plant seeds comes from a double coconut palm. A seed from an orchid has a mass of 10 to the -6 gram. That's very small. The mass of a seed from a double coconut palm is 10 to the 10th times the mass of the seed from the orchid. Your friend said the seed from the double coconut palm has a mass of about 1 kilogram Is your friend correct? Explain. So if you compared these two, seed from an orchid and that, so 10 to the 10th times the mass of the seed from the orchid. So if you took orchid's mass of 10 to the negative 6th and you made it 10 to the 10th larger, times larger, then you would get 10 to the 4th grams. Your friend says the seed from the double coconut palm has a mass of about 1 kilogram, but 1 kilogram, to my knowledge, is 10 to the 3rd. It's 1,000 grams, which is 10 to the 3rd grams. Now you might say, hey, 4 is right next to 3. That's close. But 10 to the 4th is 10,000 grams, which is 10 times larger. So I would say your friend is, 10 times off. That's pretty significant. Even though 3 is close to 4, 10,000 is not really close to 1,000. I know it's relatively closer based on what you're doing, but no, your friend is 10 times off. I'll just say that. I guess it's closer to a kilogram than a megagram or something, but not quite. All right, number 68. Critical thinking. Your school is conducting a survey. Students can answer the questions in either part with agree or disagree. Part 1 is 13 questions. Part 2 is 10 questions. I come prepared for class. I enjoy my assignments, blah, blah, blah. Agree or disagree. What power of 2 represents the number of different ways that a student can answer all the questions from part 1? So part 1 is 13 questions. In part 1, you have 2 ways that you can answer any question. So let's just break this down in just the first 2 questions, right? If question 1, question 2 were here, you have 2 ways you can represent it here. By the way, this is not a fraction. Let me do this again. 1 and 2. You have 2 ways you can represent question 1, 2 ways you can represent question 2. In total, that's 4 different ways you can represent all of those. You can say agree, 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 disagree, disagree, agree, or disagree, disagree. So you end up multiplying all these things out. Once you hit question 3, now there are 8 combinations of answers because of agree, agree, disagree, like all that kind of stuff. So you just end up, based on however many questions there are, you raise 2 to that power to answer how many different ways you can answer all the different questions for students. So for part A, there are 2 to the 13th different ways to answer questions in part 1, which I can evaluate with a calculator. Is it 8,192? Let's try that. To the 13th. 8,192. Okay. 8,192 ways. That's a lot of ways. All right, part B. What power of 2 represents the number of different ways a student can answer all questions on the entire survey? So there's a second part as well that has 10 questions. So keep in mind, you have 2 to the 13th number of ways you can do part 1. There are 2 to the 10th numbers of ways you can do part 2. And there are that many different ways you could do all part 1 and part 2 because there are that many questions in total. They're not really treated separately. You can put them together to 2 to the 23rd ways. And with that many ways, that it's large, but it's not as large that one number we wrote that one time. So I am willing to write this one out. It is in the millions, though. That's 8,388,608 ways. So you get a lot of varied answers from people, potentially. It's unlikely. See, this is why, like March Madness brackets, it's also impossible to get it right because there's so many different combinations of doing it, which would be a nice thing to talk about here. The survey changes, and students can now agree, disagree, or no opinion. How does this affect your answers in parts A and B? Well, now you're talking about 3 to the 13th ways, 3 to the 13th, and 3 to the 23rd. Now, 3 to the 23rd may be too large for this kind of thing and me to talk about. Let me just see what it looks like. Yeah, it gets the scientific notation on my calculator. But basically, now your base is 3. 3 to the 13th I can write out. But now your base is 3 instead of the other way. All right, and last question, number 69. Abstract reasoning. Compare the values of a to the n and a to the negative n when n is less than 0, when n equals 0, and when n is greater than 0, for a is greater than 1, and a is between 0 and 1. Explain your reasoning. Okay. A to the n. So base raised to power. Okay, what happens when n is... Oh, and a to the negative n. Okay, when n is less than 0, so when n is a negative number, this... Oh, compare the values. Okay, so when n is less than 0, a to the n becomes less than a to the negative n, because what happens is this turns negative. Oh, I'm sorry. And when a is greater than 1, timeout, timeout, timeout. We have to do these two different things. Give me 1 second. Part A is greater than 1. Okay, so let's say it's 2. Just to think about some things. When n is less than 0, they should have started with n is greater than 0. When n is less than 0, a to the n should be less than a to the negative n. And I shouldn't really say negative n because this number is negative, right? So think of this. 2 to the negative third is 1/8. 2 to the negative third, or 2 to the positive third, is 8. 8 should be larger there. When n equals 0, a 2 or 3 or whatever, both of these will be the same. A to the n equals a to the negative n because they are both to the 0 power. When n is greater than 0, now a to the n is the actual positive number, and a to the negative n is the negative number, which then turns it into a fraction with a 2 involved, and that would be that. Part B asks for a to be a value between 0 and 1. So think of a fraction, like 1/2. Think of 1/2. When n is less than 0, we have a to the n versus a to the negative n. Okay, consider this for a moment because it might be hard for you to hear these in your head. Think about 1/2 to the... Remember, n is a negative number now, so like negative third power versus... I'm sorry, I shouldn't have written this yet. That shouldn't be there. Consider 1/2 to the negative third power, because that was even wrong, I think, and 1/2 to the positive third power. 1/2 to the negative third power becomes 2 to the third power, which is 8, right? So the negative flips the fraction into a positive, which makes that side bigger, as long as this is a positive number between 0 and 1. So a to the n should be greater than a to the negative n here. Remember, n is not... n is a negative number in this case, and it turns this positive, but because it's a fraction, it kind of makes things work out. These should still be equal. In this case here, it still turns them into 1, as long as a is not 0, and it's not. And this one seems like it should now be the other way. So 1/2 to, say, the third power becomes 1/8, and 1/2 to the negative third power on this side would become like that 8, so this should now be larger on that side. And those should be the answers. Very abstract, of course. Okay, and that ought to do it for this one, guys. So thank you for involving yourself with these. The next two ones, I think the next one's on radical properties, and then exponential functions is left for section 1.6 for chapter 1. So that ought to do it here. This is Mr. Robinson. Take care. I will see you in the next one.